Hi, I'm here to talk today about correlation, regression, trend lines, and moving averages. Chapter 4 from the current stat course. Um, Let me start off by talking about correlations. This is a little bit different than what we've done so far in the class. What a correlation is the mathematical relationship between two sets of data. If you have a single set of data, you can't do a correlation. You have to have two sets of data to do a correlation. So it's a relationship between two sets of data. And part of what they're looking at is how do the sets of data co-vary? Literally, what we're looking at is if in this set of data, a number gets larger, in this set of data, is the corresponding number the same or larger or smaller? And it's trying to figure out what the relationship is between those two sets of numbers. Generally, a correlation has to be between a positive one and a negative one. That's the full range of them. A positive one means that if a number is two steps up on this set of data, it's going to be two steps up on this set of data, or maybe four steps up. But however much something goes up on this set, there's going to be a lockstep response for the other set of data. They're going to be exactly the same. In real life, correlations of positive one and negative one almost never happen. You never see those things. A high correlation typically is something like a 0.9 or even a 0.85 is considered a pretty high correlation. A negative correlation means that for this set of data, a number goes up, and when this data goes up here, it goes down here. So the larger this number, the smaller this number is. Positive correlation, this one goes up, this one goes up, then this one goes up. Negative correlation, this one goes up, this one goes down. Zero correlation means a change goes on in here, and over here it goes, who cares? There's no relationship basically between what happens with this set of data and this set of data. Correlations don't prove anything. That there's a correlation between two things does not mean that one causes the other. Though interestingly, a lack of correlation suggests that there is no relationship. Sometimes what happens is you get a correlation between two things, and they're actually both related to a third thing, which you don't happen to know about at the time, but so you're not quite clear about it. We look at correlations because they suggest relationships between numbers, or between data or concepts, whatever those things happen to me. Let me tell you something. Let me try and make that more concrete for you here. I don't know that you folks know this, but it's worth being conscious of if you don't. I pulled this up recently from a stat class, one of my summer stat classes. What I see is actually have names over here to the left-hand side, which you don't see. I'm not giving any student names about this stuff. But over here, what I have is this tells me how many hours each student has spent online in the course since the beginning of the course. This person spent almost 30 hours. This person spent about 5 hours. This person spent about 10 and a half hours. This person spent almost 118 hours so far. This person spent about 6.5, about a little over 7. This one spent about 3.5. I have that information, and I'm kind of going, so what does that tell me exactly? And I was curious about it because I consider the number of hours a student spends on time as an indicator of student engagement. Now, it doesn't mean that that's the measure, that this is what student engagement is. It's an indicator. I read something interesting that recently, that a line that really caught my attention, that said, the finger that points towards the moon is not the moon. It's an indicator of where the moon is. And you shouldn't you shouldn't confuse the finger pointing at the moon with the moon. They are different things. These numbers are indicators. And so I started wondering about, from last semester, actually, I'm thinking about this and saying, I wonder if students who spend more time online do better in terms of grades or outcomes in the class. It would seem logical that they do, but is it true? Well, let me show you what I found out in the process. Last semester, I looked at students and I checked how many hours they spent online versus what grade they got. And here's how many hours they spent online, and here's what grade they got in the class. Somewhat as you would expect, folks that spent less than 15 hours an entire semester online, 2 got F, 1 got a D, and 1 got a C. Now, the interesting person to me is who's this person who got a C, and I can tell you some things about that. On the other hand, and then this is increasing number of hours by 5-hour units here. You may have noted, think of this how I created my categories. And I got my Tupper categories more than 55. And then I looked at the grades. And generally, as the hours increase, there's some increase in, this is actually not grades, but how many points they got overall in the class. And there's actually, what I found is the average number of hours the students spend in my class during a semester was 34.5 with a standard deviation of 26. That's a large standard deviation, by the way, I would note for you. Given an average, that's a large standard deviation. The range is between 4 and 106 hours per student. Interestingly, I tried to find the correlation between these things, and the correlation is a 0.43. Now a 0.43 is not a very high correlation. It's only a middle correlation. And I kind of went, I wonder what that means. I don't know what, I know as a teacher what I'm supposed to believe. And what I'm supposed to tell you is, if you work more hours and work harder at this, you will do better. Maybe. My data here would suggest maybe, maybe not. And in fact, there's not a real good relationship between those two things. Now, there's some, what I appreciate is knowing there's something about the students in the class. I have students, somewhere like this class, I have students who come to my statistics class who had an A in advanced algebra in high school, took a college level statistics class, and either didn't complete it or they completed it, but it wasn't valid for transfer to Northern Vermont University. So they're basically taking a statistics class all over again. It might make sense to you as it does to me that this person probably doesn't have to spend a lot of time working in this class to pass it. This is something that the person has a really strong background and may have actually had one or more statistics class previously to my class. So they shouldn't have to spend as much time to do well in the class. On the other hand, I get some students, and the one I showed you earlier had over 100 hours, and more than one person that. I often get folks who's like, they really want to learn this, and they've never done well in mathematics. So some people are prepared to come in and really work hours, and work a lot of time at class. And even then they may not get an A, but they pass, and they're often they say, and I get it now, I've got this stuff. They're learning statistics literally for the first time in some cases. And it takes more time to do that than it was for somebody who's had the class and sort of relearning things as they go. So there are differences in this. The correlation suggests that there is a relationship, that the more time one spends, the better one tends to do, but it's a weak relationship. When I get a 0.43 correlation, I'm going, it's a weak relationship. There is some, but it's not real strong. If I did a correlation and I got a 0.93 relationship correlation, I would go, and that's a pretty strong correlation. That suggests these things are very pretty much in sync with each other. even a negative 0.93 also says there's a pretty strong correlation. But as this one's going up, this one's going down, and this one comes down, this one goes up. I mean, that's what the correlation, it's the opposite direction of movement when you get a negative correlation. And a zero correlation, again, means what happens here doesn't tell you anything about what's happening over here. Correlations are useful indicators of things. They are, however, the finger pointing at the moon. They are not the moon. Just because you have a correlation does not mean you have a causational relationship. Correlations, they co-vary. It doesn't tell you anything about whether or not there's a causation. Now, that you got to be careful of that, because people will often end up saying, well, you know, there's a correlation between this and this, therefore you should do such and such. And it's like, maybe, maybe not. I think one needs to be very careful about understanding what a correlation really tells you. It's the finger, it's not the moon that the finger is pointing towards. Once you get a correlation, one of the things that comes up in a correlation are a thing that they call trend lines. And let me see if I can show you a trend line here. Where's my trend lines at? Can't find it. Ah, no, that's not it. Well, let me do it there. Let me go here. What I did with the hours versus points earned in the class is I developed what is called a scatter plot. That's what this thing here is. It's a scatter plot. And the correlation is 0.43. This is what those same numbers I showed you earlier looks like in a scatter plot, with the points that the people earned down here at the bottom, the hours they spend in a class up there right here. There's a thing called a trend line. And let me see if I can get my trend line here. No, that's not it. Up, trend line. Now, a trend line, the more formal name for a trend line is a least squares line. Now, there's a point where I remember talking to my youngest daughter about this was I was tutoring her in statistics, and I said, now this is really exciting. And she gave me one of these looks and goes, you are such a nerd, Dad, that you could find this exciting. A least squares, one of the things this line here does is this says, this is the best line that we can draw for this thing. Now there's other lines you could draw potentially for it. You can draw a really wide variety of different kinds of lines. Let's see if I can actually draw. I mean, I could say, now if I want to do a trend, I think the trend line should be like this. Now I might choose that, but how do you know which is the best trend line for it? Well, it's determined mathematically. Once you've determined a trend line, I'll show you what that formula looks like here in a bit. You go through and say, okay, at this value of X, the trend line says I should have this value of Y. What's the difference between this point and this point on the line? You take that and you put that number over here. And then you do the same thing here. It's like real value for this value of X was here. Trend line says it should be here. Take that number and put it over here. You do that for every one of these lines. Here's what I found so exciting, and my daughter thought was such a nerdy thing to be excited about. You add those things up and it'll come to 0 every time. I think that's pretty fascinating myself. The thing is, and what they do instead, because some of those are positive and some are negative. Here, I suspect it looks like you get a lot more negatives. If you do this and you square the numbers, some lines are better here than others, and that better in the sense that they give smaller, the sum of the squares is smallest. And that's what you're looking for. It's what they call a least squares line. You take the differences between your projected, let me get that out of here because it really is not true. This line here is like, if you put this line in and you do the projections against it, you add them all up over here, and that, again, the sum would be 0 down at the bottom here. That sum's going to come up 0. But then what you do is you square them. You take this line here and you multiply it times itself, and you sum it out here, and you'll get a number, and it'll be a positive number because when you square things, the sum actually always comes up positive. Different lines will give you different numbers mathematically, and I would go through the proof of this if you were really interested in being bored. Mathematically, the trend line is the least squares line. It's the line here that you draw in that the differences between the actual values, x of whatever this is versus y, which is whatever this value is, minus this line, this distance here, you take that number, you square it, gives you the least squares sum. And that's what a trend line is. It's the least squares line. And those are really useful because it gives you a sense of what's the trend of the data. Let me show you a different one here. It's not showing up. I don't have it. Oh, it gets someplace else on my computer. That isn't showing up easily. I really like working with trend lines. And the reason I like them is because they show me how data tends to move. There is, in fact, a formula for a trend line, for a line. And the formula is y equals mx plus b. The y value is equal to your x value multiplied by something, and that's a slope. That's what the slope of a line is going to be, plus b. B is what's called the y-intercept. What happens is you have an x value here, for instance, and some y, some slope says, okay, let's multiply this number times whatever this slope is, and then add b into it. B is this point right here. When x is equal to 0, m times x is 0, so it's just b. So there's a point here. This is what's called the y-intercept. It's the point when x is equal to 0. Where does the line cross the y-axis here? If I get a single point out here and I multiply x times that and add b to it, I'll get a second point, say right here. At that point, I've got 2 points. And what that says to me is, okay, my line's going to look something like, if I could draw it straight, it would look like that. This looks that way because I can't draw a straight line. But if you do away with the fact that I can't draw straight lines, that's this level here, how much this goes up or down is the slope of a line. This point here is equal to b, which is the y-intercept. You may say, well, okay, well, it's a lot more algebra than I really want to know, Steve. It's important to get a sense of that because those lines give you a sense of which way the data is trending over time. And that's what we would spend a lot of time looking at. Sometimes it's called a regression line. Sometimes it's called a least squares line. It's the number that is the best predictor of y given x. When I have an x value, I find a trend line, a regression line, a least squares line. Those are all synonyms. And that line gives the best predictor of what the Y value is given a specific X value here. And that's an important thing to get a sense of. It tells us an awful lot. In Excel, what I do is I show you to some extent how to compute that. And Excel does it for you, which is just absolutely marvelous. And some of the Excel videos this week go into that much more. I want to show you one other kind of trend line that I think is really useful and particularly relevant right now. There's a thing called a moving average line. And I don't use it. Normal chapter, I don't do this here, but I'm going to do it this semester because it's a short chapter. This is COVID cases in Vermont. And the vertical lines here are the actual number of cases in a given day. As you can see, they vary a fair amount day to day. They're up and, I mean, here is, what is that, like, looks like 22 or 23. Up here, it's closer to about 50. I mean, it almost doubles literally in a day. The reason that they have that much variation in it is because, you know, sometimes somebody comes in and gets tested or the positive results come back at 9 o'clock in the morning. And then for whatever reason, the person doing testing is out, has to go to take their kid to the dentist. They don't get to the rest of the next day. So they come in the next day and they do a bunch of them the next day and get them all done. There's some things that cause a variation. Some of the low points on here tend to be weekends because people often don't get tested on weekends. You know, they put it off till Monday morning or something. So there's variation in the day-to-day values of these things. There is a thing called a 7-day, here that we use, what they're doing here is a thing called a 7-day moving average. What that does is it takes 7 days in a row, 1, 2, 3, 4, 5, 6, 7. And the moving average for this day is this date plus the last 6 days. What's helpful with that is that removes some of the variability of the actual day-to-day numbers. A moving average gives you the trend, which here, for this part of the thing, is really clearly uphill, but it removes some of the day-to-day variation. So that you happen to get a really high number here, it's like, yeah, that pulls numbers up for a while, but it doesn't jump the numbers, the average way up here. And what happens here is you get a sense of like, oh, well, this number here is not that much different than what that's been over here, but the average here is starting to move down until down here the average is 2. Let me give you a different one of those to look at. This is the same sort of data, again, with a 7-day moving average in it. And what you tend to see is, again, and I think this one's actually in North Carolina. This goes to the same date, for instance, as the last that I showed you was. And whereas in Vermont, the trend line had started going down. At this point, the trend line is still going up in North Carolina. So they're seeing more cases. They have probably more variability than we do. They go from as little as 100 to almost 600 in a day. So they have a variation of 500 cases through one day to the next. That's a huge variation by Vermont standards. For them, it's not a lot. It's not so much. But the 7-day moving average tends to give you a sense of saying, I'm not going to get distracted by a low point here or a high point here. I'm looking at what this line looks like over time. And what the line looks like over time is it's still on an upward trend. Moving averages are, you take the last, in this case, 7 values you have and you add them together, and that becomes the value for that day. The next day, you dropped off the first one and you add a new one on the other end, that becomes the moving average for that day. And you plot the moving averages. And it's a way of of getting more timely data that you ultimately have removed some of the variation within. So the variation doesn't tend to, I mean, it's really hard to get a sense here. Just if I was pulled out this dotted line and looked at stuff just from, say, here to here, it would be hard to look at the data itself and say, so what's happening here? And the trend line gives you a way of getting a sense of that. It's a really useful tool. And it's getting a lot of use during this time. I want to note that somewhat arbitrarily here, they're using a 7-day moving average for the COVID numbers. You could do a 5-day moving average, or you could do a 3-day moving average, or you could do a 10-day moving average. The longer your span, the less the variability tends to impact it. There'll be much less variability. You still get a trend, but there'll be less variability in a 10-day moving average. You go to a 3-day moving average, you'll get a lot of variability in the line. And to some extent, you have to experiment with. There's no right answer about what the length of time should be for different things. The moving average is used extensively with time-based data in which there is a fair amount of variation, but in which you're interested in looking at trends. So I've talked about two different kinds of trend lines here. One is the least squares trend line, which is a straight flat line, maybe uphill, maybe downhill, maybe level, but it's a straight flat line. And if you're looking at data over time, that's really a useful thing. Or if you're looking to see how data relates to each other, that's really useful. Time-based data with lots of variation in it, a 7-day moving average is a much more useful way of trying to get a sense of what's the trend, what's happening here. I think that's all I want to say about this so far. And that's a good, I think a good brief overview of stuff. There's a lot of stuff in the readings this week, a lot of useful tools in Excel for working with this stuff. And I encourage you to look that over and ask questions as it comes up for you.